Hi, I'm David Thornton with the Clemson Biofuels program, and we're going to continue with some of our lessons on quality control testing for home biodiesel production. And the test what we're going to do right now is called a soap titration. This is testing for soap, which is a side reaction that occurs during the biodiesel reaction. In particular, it happens because free fatty acids that are in our oil are going to bind with our catalyst, potassium hydroxide, which will also produce some water in that acid-base reaction, and the result is going to be a aqueous soap. So soap being potassium-based and most likely with oleic acid is going to be potassium oleate, and if soap is in our finished fuel, it's not going to burn very well. So those potassium ions, they can contribute to coking or deposit buildups on injectors or in your cylinders, and it's not going to combust very well. It'll likely clog the fuel filter. So we're going to avoid that through some basic quality control testing. The method is very similar to the free fatty acid titration that we did earlier, except this time, instead of adding a base titrant to an acid oil, we're adding a acid titrant to an alkaline biodiesel product because it has this potassium-based soap dissolved into it. So we start by taking a representative sample from our process tank, and this is taken directly after the biodiesel reaction. So glycerol has been removed, we have biodiesel left in the reaction tank, and we pull this sample from it. We'll also just shake it up to make sure it's homogeneous. We'll start by tearing the weight of a 250 milliliter beaker, and then adding a 4-gram sample of our oil. We then record that value. We're then going to add 50 milliliters of a solvent, just like in the other one we used isopropyl alcohol, except this time we're going to use acetone. It's just a little better at dissolving our sample. We'll then take a clean stir bar and add in 4 drops of our color indicator. This one is called bromophenol blue. When a solution goes from being alkaline to slightly acidic around 6.8, this solution turns from blue to a bright yellow. We call it a permanent yellow. So 4 drops. Sometimes you can put an extra one if you don't see a lot of color change. We'll just give it 1 more. And then we take it over to our titration station, put on a gentle stir. And can you see the color of that there? It's a bluish color right now. And with each drop it'll turn a little more green and then yellow, and eventually what we call the permanent yellow means there's no trace of green or blue left in it. Before we get started, we've got to write our initial volume of our titrant, which is going to be 25.10. I'm going to slowly add drops of the titrant. Now it's really starting to turn yellow, and that you can see now. This is our permanent yellow here. So I'm going to record the final volume of titrant. .7. And then we can solve with a similar equation. In this equation, we take the change in the volume of titrant, so the amount of titrant used, minus a blank. The blank in our case is 0.15 milliliters. That means it required 0.15 milliliters of our 0.01 normal hydrochloric acid solution to neutralize any alkalinity that was in our acetone sample. So this is just accounting for the alkalinity of the acetone sample on its own. Alright, so now that we've gotten our data on the volume of titrant, that's our 0.01 normal hydrochloric acid solution, the volume required to neutralize the soaps in our approximate 4 gram sample of oil, we can go ahead and solve the equation for our soap concentration, which will be in parts per million soap. So our T minus B minus our blank, which is basically a test that we do that determines what the alkalinity of our acetone is so that it doesn't impact our final result. So we've determined that it requires 0.15 milliliters of this 0.01 normal hydrochloric acid solution in order to neutralize any alkalinity in our acetones. So we're going to subtract 0.15 ml. Multiply this by the normality of our titrant, which is hydrochloric acid. Multiply this by our factor, which is our conversion factor using potassium oleate's molecular weight. All of that will be over the weight of our sample. And that will give us, get the rest of that solution there, 2,530 parts per million soap. And that soap again is potassium oleate. So this would be about 0.25% of our total solution is soap. It's far too much soap to run in an engine. Soap will not combust. It'll leave deposits on injectors, in your fuel tank. It could clog a fuel filter. So it's just not part of our combustible fuel, and we need to get it out of there. So the process we're going to now is going to evaporate out any moisture or methanol remaining in the fuel, for which the soap will no longer be able to stay in solution, and it'll settle to the bottom of our tank. And after this period, which is part of our washing process, our post-reaction processing, after this period of sparging where we pump air bubbles to evaporate that water and methanol, we're going to take another soap sample. So this will be tomorrow, and we should see a decrease in the soap number. Once we get it down to a level of about 1,500 parts per million, we can then run it through our final polishing fuel phase, which will remove that down to an undetectable level of soap. And that final phase is called ion exchange. And this is where the potassium ions that are in this soap are going to get reacted into the ion exchange media, and in turn the oleic acid part of the soap molecule will be released. So that's the actual exchange of potassium ions for basically these acid ions. And that's going to affect the final fuel quality as far as its acidity. So in our case here, we have to have parts per million of soap below 1,500 so that we don't end up with too much acidity in our final product.